You've heard the stories about spider silk. For centuries, it's been talked about like a miracle of nature, this legendary super material. But you have to wonder, is the legend actually true? Well, today we're going to unravel that very story.
And this is the big one. This is the claim that really cemented the myth. The idea that a single strand of spider silk, no thicker than a pencil, could stop a jumbo jet cold in midair. I mean, it sounds impossible, right? Like something out of a comic book, but is it?
That is the exact question we're here to answer. And as it turns out, the truth is, well, it's a lot more complex and, honestly, way more fascinating than the myth. So let's dive into the science.
Okay, so to really get to the bottom of this Boeing myth, we have to start with the basics. We have to talk about what strength really means. Because in the world of material science, that word isn't as simple as it sounds. And that's exactly where all the confusion begins. I'm sure you've heard this one before. Spider silk is 5 times stronger than steel. It's a great soundbite, it's easy to repeat, but you know what? It isn't the whole story. Not even close. The real magic of this stuff is about so much more than just raw strength. So here's the crucial difference. You've got tensile strength, which is basically how hard you can pull on something before it snaps. Pretty straightforward. But then you have toughness. And toughness is a whole different beast. It's about the total amount of energy something can absorb. It's a combination of being strong and being stretchy. Just look at how they're designed at the molecular level. A material like Kevlar has these really rigid, highly organized molecules all lined up, which gives it that incredible raw pulling strength. Spider silk, though, it's different. It's a much more complex blend, almost like nature engineered it to do 2 jobs at once: be strong and be flexible. And here's what that actually looks like. When you compare the sheer amount of energy it takes to break these materials, the story becomes crystal clear. Yeah, Kevlar might be stronger in a simple tug of war, but spider silk is massively tougher. It can soak up a huge amount of punishment by stretching before it ever fails. It's not just strong, it's resilient. So we know spider silk is unbelievably tough. That brings us to the next obvious question. How? How does it do that? Well, to find out, we have to dive deep, all the way down to the molecular level, to see what makes this fiber so special. The secret, as is so often the case in biology, isn't some magic ingredient. It's hidden in the structure itself. It's a masterpiece of natural engineering, something that's been perfected over millions and millions of years of evolution. If you could zoom way in on a single strand of silk, you'd find that it's not just one solid substance. No, it's a composite material. It's this brilliant mix of hard, crystalline sections that are embedded inside a flexible, almost gooey, unstructured matrix. Think of it like this. It's like nature is weaving with rebar and bungee cords at the same time. The hard, crystalline bits act like the rebar, giving it immense strength, and the flexible parts, they're like a web of bungee cords, giving it that incredible stretch. It's the perfect combination of both. And what's truly mind-blowing is that the spider makes this stuff on demand. Inside its body, it's basically just a liquid protein soup. But as it's being spun out, the spider uses these incredibly precise, controlled changes in pressure and acidity to instantly forge that liquid into a solid, super tough fiber. They're master nanotechnologists. Now, with a material this amazing, it's absolutely no surprise that scientists have been trying to copy it for decades. But as it turns out, replicating nature's blueprint, well, that's a whole lot harder than it looks. So why aren't our jackets and our car tires made of this stuff? Well, here's the first huge problem. You can't farm spiders. It's just not possible. Unlike nice, docile silkworms, spiders are territorial. They're predators. They're cannibals. You put a bunch of them together, you don't get a silk farm, you get a spider battle royale. Mass production from the source is a complete non-starter. So scientists had to get really creative. They've come up with some pretty ingenious ways to essentially program other organisms, we're talking everything from E. coli bacteria to goats, to become these little microscopic silk factories, producing the raw proteins for us. One of the most promising techniques is basically a clever bit of biohacking. You take the gene for spider silk, the instruction manual, you insert it into a harmless virus, and then you use that virus to infect insect cells. The virus hijacks the cell's own machinery and turns it into a tiny factory that does nothing but churn out silk protein. And this is a peek at how it actually works in the lab. To figure out which cells are successfully making the protein, scientists attach a little green fluorescent marker. That means any cell that's doing its job will literally glow green. A machine can then automatically sort and collect only those glowing cells, making the whole process way more efficient. And this isn't just science fiction stuck in a lab anymore. This is happening now. You have pioneering companies like Spidroin Inc. and Craig Biocraft who are taking this science and scaling it up, working to bring synthetic spider silk from the laboratory to the factory floor.
So, where does this all lead? We've busted the myth, we've explored the incredible science that's way more interesting than the myth. Now, let's look at what the future of this material really truly holds.
So here's the key takeaway, the most important thing to remember. Forget about stopping airplanes. The real potential of spider silk lies in its unique combination of properties. It's not just ultra tough, it's also incredibly lightweight, and this is a big one, it's biocompatible. That means our own bodies accept it without a fight. And that amazing combination just unlocks a whole world of possibilities. I mean, imagine medical sutures that are stronger than steel, but just safely dissolve in the body when their job is done. Or scaffolds that can help nerves actually regrow after an injury. Or body armor that's lighter and more flexible than Kevlar. The applications, they're nothing short of revolutionary. Ultimately, the story of spider silk is this powerful reminder that nature is the original and still the best innovator. Its R&D department has had a 3.8 billion year head start on us. It just makes you wonder, doesn't it? What other incredible materials, what other world-changing secrets are just waiting out there for us to discover?
Don't go anywhere, hit subscribe and we continue.
You know, when we think about the perfect fuel, what are we really looking for? I mean, it's got to be powerful, right? It needs to be renewable, something that won't run out. And, of course, it has to be clean. We've spent decades chasing the sun, the wind, the very heat of the earth. But what if? What if the answer was right under our noses the whole time, hiding in plain sight inside these tiny, microscopic power plants? Yeah, let's dive into the incredible world of algae.
Okay, to really get a grip on the kind of potential we're talking about here, you just have to look at these numbers. And no, that last one is not a typo, seriously. So you've got soybeans, a pretty standard biofuel crop, right? It gives you about 450 liters of oil per hectare in a year. Then you have oil palm, way more productive, but also kind of controversial. That gets you almost 6,000 liters. But then you have algae. In the right conditions, we're talking about a mind-blowing 50,000 liters. 50,000! That is almost 10 times more than the next best thing. It's a completely different league.
So yeah, green gold. That's what people have been calling this stuff for years, and now you can see why. We're not just talking about pond scum here. Think of them as nature's tiniest, most powerful little solar-powered oil factories. The promise is just huge.
So why algae? I mean, beyond that insane oil yield. Well, the implications are just massive. Remember the big problems with early biofuels? The whole food versus fuel debate? How they competed for farmland and fresh water? Well, algae just sidesteps all of that. It can grow on land that's useless for farming. It's not a picky drinker either. Freshwater, saltwater, even wastewater, it doesn't care. And here's the kicker, the best part. Its favorite food is carbon dioxide. It literally eats pollution to grow, turning our waste CO2 into fuel. On paper, it's the perfect solution, isn't it?
And when you look at how it works, the whole process, it seems so simple, almost elegant, right? You give it the basics, a little sunlight, some CO2, a few nutrients. You let the algae do its thing, grow like crazy in a pond or a bioreactor. Then you harvest it, you squeeze out the oil, and boom, you convert that oil into biofuel. And you're not even done. The leftover stuff, the biomass, that can become animal feed or fertilizer. It's a perfect little circle. Simple, clean, efficient. But, and there's always a but, isn't there? If it's all so perfect, so straightforward, why aren't our cars running on this stuff right now? Well, this is where things get really interesting. This is where we uncover the hidden truth behind the promise.
Yeah, exactly. What's the catch? It's the one question that has haunted this entire field for decades. With all this potential, there had to be a catch.
And here it is, the brutal, simple truth that brought the whole green gold rush to a screeching halt. It often takes more energy to make the fuel than you get from the fuel. Let that sink in. All the energy for the pumps, the harvesting, the drying, the extracting. When you added it all up, for a lot of the early projects, you were in the red. You were actually losing energy. There's a term for this. It's called the net energy ratio, or NER. And it's actually pretty simple. Imagine spending $2 to get $1 back from an ATM.
You wouldn't do it, right? It's a losing deal. That's an NER of over 1. For any fuel to make sense, you have to spend less than $1 of energy to get $1 of energy out. Your NER has to be below 1. And for the longest time, algae was on the wrong side of that line. It wasn't an energy source, it was an energy sink. And it wasn't just one thing, it was a whole mess of tough, real-world problems. First, think about harvesting. You've got trillions of microscopic cells floating in these massive ponds. Getting them out of the water takes a ton of energy. Then you've got this prized, super productive algae strain you developed in the lab. The second you put it in an open pond, it has to fight off all the local wild stuff that wants to take over. It's a constant battle. And on top of all that, you have to constantly pump in nutrients and CO2, which costs money and, you guessed it, more energy. The dream was basically running face first into a brick wall of physics and economics.
Okay, but this is where the story pivots. This is where it gets really cool, because the smartest people in the room started to realize they were thinking about the problem all wrong. This wasn't a farming problem, it was a biology problem, a puzzle. And the solution wasn't better tractors, it was better DNA. The goal shifted. It wasn't about farming algae anymore, it was about hacking.
And this really captures that huge shift in thinking. The old way, it was basically an agricultural approach. You'd send scientists out into the wild to collect thousands of different algae samples, hoping you'd get lucky and stumble upon some kind of natural wonder strain. The new way is a complete 180. It's a biotech puzzle. Forget finding the best one, let's build the perfect one. It's about getting into the source code of the algae and engineering it to be exactly what we need.
It's really the difference between being a gold prospector, panning a river and hoping for a lucky find, and being an alchemist who can literally design the gold from scratch. We stopped just searching for the answer and started building it. A total move from discovery to design. So what was the key that unlocked this door? Well, it's a piece of technology you've definitely heard about, CRISPR. Think of it as a pair of tiny programmable molecular scissors. For the first time, scientists had a tool precise enough to go into the algae's DNA and make specific, targeted edits.
So, how did they use this genetic shortcut? Well, check this out. Researchers at Synthetic Genomics, working with ExxonMobil, did some amazing detective work. They found that algae have a specific gene that works like a safety brake for making oil. It's a survival thing to conserve energy. So, using CRISPR, they were able to sneak in there and just cut the line to that brake. They took the handbrake off. And the result? Absolutely incredible. The algae's oil content, as a percentage of its own body weight, more than doubled. Just like that. They didn't need better ponds or fancier pumps. They just built a better, smarter algae.
I love this quote. Plants were doing solar efficiency long before engineers got the memo. Now engineers are returning the favor. It's so true. Nature had billions of years to perfect this whole photosynthesis thing. Now we're just coming in and, giving it a little tune-up, helping these tiny guys work smarter, not harder.
But okay, engineering an algae cell that's packed with oil is awesome, but it's only half the fight. Because remember our old enemy, the net energy ratio? It doesn't matter how much oil is in there if it takes too much energy to get it out. And that brings us to the second huge area of innovation, the extraction. So the old way of getting the oil out was messy. It involved harsh, toxic chemicals like hexane. Not great for the environment, and it took a ton of energy to get the solvent back out of the oil later. But the new way? It's something straight out of science fiction. It's called supercritical CO2. You take regular old carbon dioxide, pressurize it until it gets into this weird state where it's not quite a liquid, not quite a gas, and in this supercritical state, it becomes this amazing, perfectly clean solvent. It just flows through the algae, grabs the oil, and leaves everything else behind. No harsh chemicals, way more efficient. And just look at the difference it makes. This advanced extraction process can take that dark, sludgy, raw algae oil, full of gunk like chlorophyll, and turn it into this beautiful, clean, golden oil that's ready to become fuel. It's not just cleaner and safer. The most important part is that it's way, way more energy efficient. It's helping us finally win the fight against that pesky net energy ratio.
So, let's bring it all together. We've seen the incredible promise, the frustrating walls it hit, and now these brilliant breakthroughs. So what does this all mean? What's the future of this fuel really look like? Okay, so let's boil it all down. What's the big takeaway here? First, the whole game has changed. We've moved from trying to solve this with brute force farming to solving it with elegant, high-tech bioengineering. Second, we've learned that success isn't about one magic bullet. It's a two-pronged attack.
You have to genetically engineer a better algae, and you have to use advanced science to process it efficiently. The amazing potential of algae is finally being unlocked, but it's not a farming story anymore. It's a story about cutting-edge science. And that leaves us with one last big question. For literally billions of years, these tiny organisms have been quietly turning sunlight into energy, just doing their thing. Now, for the first time ever, we have the tools to actually work with them, to rewrite their code and unlock their full potential. It's been a long, tough road for sure, but the science is finally catching up with the dream. So the question isn't really, can we get fuel from algae anymore? The real question is, how fast can we get good enough at this to power our world?
Don't go anywhere, hit subscribe and we continue.
Have you ever stopped to think that the most sophisticated technology on this planet might not be in a lab in Silicon Valley, but right outside your window? You know, the idea that the quiet, patient growth of a tree could hold a secret that completely upends our entire digital world. Okay, let's really get into this. I mean, if you really look at the natural world, it's an absolute masterpiece of engineering, right? Every forest is this incredibly complex, decentralized network. Every single leaf is a hyper-efficient solar panel. Plants were doing solar long before we even got the memo. For billions of years, nature's been running the biggest R&D department in the universe. So what if we could finally start to understand its language? What if we could merge our tech with its ancient, powerful living systems? Now, to understand just how revolutionary this is, we've got to go back to basics. We need to talk about the humble transistor. First invented way back in 1947 at Bell Labs, it's basically the fundamental atom of our digital age. It's just a tiny microscopic switch. That's it. By turning on and off, it creates the ones and zeros that run, well, everything. The phone in your hand, the laptop on your desk, the entire internet, it's all powered by billions upon billions of these tiny little switches. But here's the catch. All that incredible digital power comes at a pretty steep price. You see, the foundation of all of our modern electronics is silicon, and our dependency on it has a massive and often invisible environmental cost. So let's just lay it all out. On the one hand, you have our current system. We have to mine non-renewable silicon from the earth. The production process, it releases this nasty cocktail of powerful greenhouse gases, things like nitrogen oxides and fluorinated gases that are literally thousands of times worse for the atmosphere than CO2. And when we're done with our gadgets, it all adds up to this enormous mountain of e-waste that's a nightmare to recycle. But what if the alternative was something you could grow? Something that's totally renewable, biodegradable, and could lead to electronics that you could literally just compost. And that leads us to this really profound question. It sounds like something straight out of science fiction, but it's quickly becoming a scientific reality. What if we could shift from manufacturing to cultivation? Could we literally grow the next tech revolution? Well, believe it or not, the answer starts with a team at Sweden's Linköping University. They took on the absolutely wild challenge of trying to make a piece of wood think. Their goal was to build a working electronic switch from one of the most common materials on Earth. So how in the world did they pull this off? Well, the process is actually surprisingly elegant. First, they started with balsa wood. Why balsa? Because its structure is incredibly porous, almost like a natural sponge full of tiny, hollow channels. Next, they used a chemical process to wash out the lignin, that's the stuff that makes wood rigid and strong. Getting rid of it basically opened up those internal channels even more. Then came the magic step. They soaked the wood in a special conducting polymer. You can think of it like liquid wiring that seeps into all those empty channels, turning the entire piece of wood into a conductor. And from there, they could just assemble 3 of these treated pieces together to create a real working transistor. And this wasn't just some lucky guess. The team was super methodical about it. As one of the lead researchers, Van Chin Tran, pointed out, balsa was the hands-down winner. It conducted electricity way, way better than other woods they tried, like pine or ash. And what that tells you is that this wasn't about reinventing the wheel. It was about realizing that nature had already done most of the design work for them. And this is where the story truly changes. Because here's the detail that most people miss. This project was never really just about making biodegradable smartphones. No. The wood transistor is a proof of concept for something so much more profound. It's about building a bridge, a direct bridge between our digital world and the living, breathing, biological world.
I mean, look at this. This isn't a circuit board from a computer. This is a map of the molecular pathways inside a single living cell. It is an information processing system of almost unimaginable complexity and efficiency. And the wooden transistor, it's the very first step towards creating technology that can actually speak this language, that can plug directly into the intricate, organic circuitry of life itself.
This whole new field actually has a name, hybrid bio-semiconductor systems, and it represents a massive paradigm shift. We're moving beyond creating tools that we simply use, and we're heading towards creating systems that actually integrate with biology, blurring the lines between machine and organism in ways we are just now beginning to understand. If you put this on a timeline, you really see how big of a moment this could be. You had the first transistor in 1947, a total game changer. Then the MOSFET in '59, which made modern computing possible. Each step was a massive leap. Well, the wood transistor in 2023 marks the next potential leap. The moment we go from building our technology on sterile silicon wafers to potentially growing it inside of living things.
So, what does a future like that even look like, right? What actually happens when our technology stops being this cold, static object and starts becoming a living, breathing system?
The possibilities are just staggering, and they go way beyond just greener gadgets. We are talking about the potential to grow circuits directly inside the vascular system of a living tree, or creating e-plants that can sense their own needs and regulate their own health, which would totally revolutionize farming. Imagine powering an entire network of environmental sensors using only the energy a tree makes from sunlight, monitoring an entire forest for fire risk from the inside out. This isn't just about making better computers. It's about creating intelligent ecosystems. This quote from Daniel Simon, one of the physicists on the project, just captures the whole vision so perfectly. It's not about replacing nature with technology. It's about weaving technology into nature in a totally seamless, symbiotic way. We're not just talking about greener electronics anymore. We're talking about living electronics.
So in the end, it really all comes down to this. For the last 70 years or so, we've been perfecting the art of building our technology in these ultra-sterile, ultra-controlled factories. But this breakthrough asks a fundamentally different question. What if the most powerful computers of the future aren't assembled at all, but cultivated? What if the next great tech revolution isn't built in a factory, but grown in a field?
Thanks for watching. Support BioVellum by liking, subscribing, and sharing. Let's explore the secrets of nature together.